Lecture 20, Transmission or ABCD Matrix. Concerning the equivalent port representation of networks that we have seen before, so we have learned on the Z parameters. So Z parameters are useful for series connected network. And then we have Y parameters. So Y parameters are useful for parallel connected networks. And the last one is the S parameters, which are useful for describing interactions of voltage and current waves with a network. Now, for this course, we have the final one, which is the ABCD matrix, or we can call it the transmission matrix. So please consider this two-port network. So you have at port 1, V1 and I1. Port 2, you have V2 and I2. And here you have the ABCD matrix. But the difference in this diagram from the previous one that we have seen, do you notice here that the I2 is directed away from the port? So instead of I2 coming over, going into the port, this one is outgoing from the port. So this is an important point, and we will show you the reason for it shortly. So ABCD matrix is defined as V1 I1 is equal to ABCD times with V2 I2. So from the matrix, we can derive what is A, B, C, and D. So A would be V1 over V2 when I2 is equal to 0. B would be V1 over I2 when your V2 is equal to 0. C would be I1 over V2 when I2 is equal to 0. And D would be I1 over I2 when your V2 is equal to 0. So note that not all of these parameters will have the same unit. So the usefulness of the ABCD matrix is that the cascaded two-port network can be characterized by simply multiplying the ABCD matrices. Now let us look into the two-port network here. So you have the first one, the left figure. So V1, I1 at port 1, and then you have the matrix A1, B1, C1, D1. And port 2, you have V2 and I2. The second figure, you have V2 prime and I2 prime going into the ABCD matrix. So you have A2, B2, C2, D2. And finally, you have at port 3, V3 and I3. So the matrix representation would be, this is for the first figure. So you have V1 I1 is equal to A1 B1 C1 D1 times with V2 I2. And then for the second figure, you will have V2 prime I2 prime is equal to A2 B2 C2 D2 times with V3 I3. So when you have these two ports cascaded, meaning that you combine the two ports, okay, you'll have this figure. So here V1 I1 and then the ABCD matrix A1 B1 C1 D1, and then it goes out to port 2, so you have V2 and I2. So the second figure here has been cascaded. Okay, you have the second port cascaded to the first port. So you have V2 prime and I2 prime, where your V2 prime is actually V2 and your I2 prime is I2. Okay, and then it goes into the second port. So you have A2, B2, C2, and D2. And finally at port 3, you have V3 and I3. So from this figure, you have one big equation. So the matrix will be V1I1 is equal to the first matrix, which is A1, B1, C1, and D1. And then the second port matrix, which is A2, B2, C2, D2, times with V3, I3. So the matrix product in this equation as describing the cascade of the two network. So you will have A3, B3, C3, D3. Okay, this is the matrix product, yeah, which is the product of the first and the second matrix. So you have A1, B1, C1, D1 times with A2, B2, C2, D2, which will give you A3, B3, C3, D3. So when you have the matrix product here, just plug in those into the equation before. So you will have V1I1 is equal to A3, B3, C3, D3 times with V3, I3. So this is a simpler form where you have simplified the matrix. So A3, B3, C3, D3 is the simplified matrix product. So in other words, a cascaded connection of two-port network is equivalent to a single two-port network which contain a product of the ABCD matrices. Now let us look into the example. So please derive the ABCD parameters for the T network given in the figure. So here you will have the first port, which is V1I1, and then you have Z1, and then this one is Z3 with VA plus minus over here, and at port 2 you have V2 and I2, and then there's a Z2 over here. Okay, so how do you derive? So V1 will be equal to AV2 plus BI2. And I1 would be CV2 plus DI2. So to determine A, so A would be V1 over V2 when your I2 is equal to 0, meaning that your I2 is open circuit. Okay. So you open circuit port 2 so that your I2 is equal to 0. Hence, you will have VA is equal to Z3 over Z1 plus Z3 times with V1, which will be equal to V2. So this is the voltage divider. So let us look into the figure back. So when you open circuit I2, meaning that your I2 is equal to 0 now. Okay, so this port is open circuit. So you will have your VA is equal to V2, which is the voltage divider. So voltage divider would be Z3 over Z1 plus Z3 times with V1. Hence this equation here. So that's why you will have your A is equal to V1 over V2, which is equal to 1 plus Z1 over Z3. Next, B. So B is equal to V1 over I2 when your V2 is equal to 0. So when your V2 is equal to 0, meaning that you have to short circuit port 2 in order to get V2 0. Now, use the current division and you will have I2 is equal to Z3 over Z2 plus Z3 times with I1. So substitute this equation into expression B. We will have B is equal to V1 over, so instead of I2, you use I2 is equal to Z3 over Z2 plus Z3 I1. So plug in those values. And solving the equation, the long equation, finally you will have B is equal to Z1 plus Z2 plus Z1, Z2 over Z3. Now, how do you determine C? So C is equal to I1 over V2 when your I2 is equal to 0. So you open circuit port 2. There you will get VA is equal to I1Z3, which is equal to V2. So plug in those and you will have C is equal to 1 over Z3. Finally, for D is when your I1 over I2, provided that your V2 is equal to 0, meaning that you have to short circuit port 2. So use the current division, you will get I2 is equal to Z3 over Z2 plus Z3 times with I1. So D would be I1 over Z3 over Z2 plus Z3 times I1, which will give you 1 plus Z2 over Z3.